I want to do another 2D kinematics example with you that is similar to the example we just did, but a slight variation, which makes it a little more complex. So in this example, you throw a ball with the same initial velocity as in the previous example, 30 meters per second at an angle of 40 degrees above the horizontal. But this time you throw it from an initial height of 50 meters. And the ball follows this trajectory. It eventually hits the ground. And I want to go through what happens to the velocity vector at several points along this path. Remember, when the ball reaches its maximum height, the velocity is purely horizontal, and it equals the initial x component of the velocity, because the x component is constant the whole time. Gravity, the acceleration, acts in the vertical direction, pointing down. There's no acceleration happening horizontally. There's zero horizontal acceleration, so the horizontal velocity component stays constant, stays the same the whole time. So we launch with this velocity from some height, reach a maximum height where the velocity is purely horizontal, and then the y component of the velocity starts to get larger, pointing downward, and the ball continues on and eventually hits the ground. So in the previous example, it was as though we only had this much of the motion. It was as though the ball landed right here. But now, because we're starting from an initial height, it travels much farther. So let's answer the same questions we looked at last time. How long does it take to reach the maximum height? What is the maximum height? How long is the ball in the air until it lands? How far does the ball travel horizontally? And what's the velocity vector when the ball hits the ground? As usual, we're going to use our problem-solving procedure. This is a kinematics problem because that's all we know how to do so far. Let's identify our known quantities in part A. Well, we know x initial, we can assume that's 0. We know y initial, that's going to be 50 meters, because you're 50 meters above the ground. We know Vx initial and Vy initial. Those are the same values that we had from the last example, because we're launching with the same speed and angle. We know Ax, that's 0. We know Ay, that's negative 9.8 meters per second squared. And we know that Vy final at the maximum height will equal 0. So so those are our known quantities. And our unknown that we're trying to find is the time. We need to pick an equation to use. And the only one that's going to do it is this first y equation, Vy final equals Vy initial plus At. And if you're paying close attention, you might notice that we're doing exactly the same thing we did in the previous example. In fact, nothing has changed at all. When we solve this, we get the same result. Vy final was 0. We have Vy initial and At. T is negative Vy initial over A. And and it's that same number, which was 1.968 seconds without rounding, or 1.97 seconds with rounding. So the fact that we're starting higher this time doesn't make any difference for how long it takes to reach the maximum height. So let's do part B now. I won't erase those. In part B, we have the same batch of known quantities, and we also know the time that it takes to reach that maximum height. So what we're trying to solve for, our unknown quantity we're trying to find, is y final, and we'll use we have a couple options this time. We could use the second, third, or the fourth equations. And like last time, I'll just use that second one. Now this time we get a different result, because when we did this example the first time, y initial was 0, ground level, but now y initial is 50 meters. Y final is still 0. So we have 50 meters plus the result from last time, which was 19 meters. So the fact that you're on a building just means you add the height of the building to the maximum height of that projectile. That kind of makes intuitive sense, I think. All right, part C. Now, I keep saying this, but keep in mind that parts A and B have the same, refer to the same situation, where initial is throwing and final is reaching the maximum height. Parts C, D, and E refer to a different situation, where initial is still throwing, but final is landing on the ground. So we can't use all the same values in parts C, D, and E that we had for A and B. We need to keep in mind what we mean by initial and final at all times. So part C, how long is the ball in the air? Let's list our known quantities, keeping in mind our new final situation. We still know x initial and y initial. X initial is 0, y initial is 50 meters on top of the building. We know Vx initial, Vy initial, Ax, Ay. And we also know y final, because the final scenario now is when the ball hits the ground, so y final will be 0. We're trying to solve for the time, that's our unknown. So let's pick a good equation to use. We go through our list of 8 equations. We find that there is only one of them that's useful. And the only equation that does us any good is the third y equation. And I've said this before, but if you don't believe me, go through and check all 8 equations and see which one you're able to solve. with algebra, and it's only this one where it's possible to solve for t. And I have some bad news about this equation. We have to use the quadratic formula to solve it now. In the previous example, both y final and y initial were 0, and that let us solve this using some simple algebra. But now, y initial is not 0, it's 50 meters, which makes the algebra more complicated. In fact, you have to use the quadratic formula to solve it. So let me derive the quadratic formula for this situation. See if you can follow along with my algebra. First, I'll move these terms around. So I subtracted y final from both sides and then just wrote the terms in a different order. And now, t is my unknown variable. So I'm going to identify these coefficients of the powers of t as my parameters in the quadratic equation. at squared plus bt plus c equals 0. So the quadratic equation has a solution given by the quadratic formula. So let's replace that generic formula with the particular terms that we have in here coming from kinematics. So B was our Vy initial. A was 1/2 times that Ay acceleration, and the C term was y initial minus y final. Divide all that 2 times that a term, 1/2 ay. And now it's your job as physics students to plug in all the numbers here. And I'll show you what the answer is. And you need to make sure that you're able to use your calculators correctly and get this answer out. Well, there's actually 2 solutions to the quadratic equation. Only one of them is the correct answer, though. So these 2 solutions are 5.712 seconds and negative 1.784 seconds. So only one of these makes physical sense. They both work mathematically, but only one makes sense in nature. The positive answer makes sense because when you have a positive time, that's saying the ball hits the ground after you threw it. It hits the ground 5.7 seconds after you throw it. The negative answer would be saying the ball hits the ground 1.78 seconds before you threw it. That doesn't make any physical sense. So we eliminate this answer. The negative answer does have a mathematical interpretation. It's if the ball had been launched on a trajectory from ground level such that its path matched the path I drew in this problem, then it would take 1.784 seconds to go from ground level to 50 meters. But that didn't actually happen in this problem, so this answer doesn't have any physical meaning. And we choose this one. And we can write it 5.71 seconds if we want to round to correct significant figures. Okay, let's do part D. Part D. How far does the ball travel? All right, we still have all these known quantities, and we have another one. Now we know t, because we just found that in part C. So how far does the ball travel? That means we're looking for x final. So we should use one of these x equations, and just like in the previous example, it doesn't matter whether we use the second equation or the third equation. They'll both get you there. Let's use the second one because it's a little bit simpler. Actually, let's use the third one. The third one's a little simpler. The third one's nice and simple because the acceleration in x is 0 and x initial is 0. So we just have the familiar relationship, x equals v times t, and we use our same vx from last time, and we use the t that we just found in part C. So those were 22.98 meters per second and 5.712 seconds, which gives you 131 meters. In the example we did before, the ball traveled 90.4 meters, so it's gone 40 meters farther, almost 50% farther this time, because it got launched from a higher initial height. All right, last question. What is the velocity when the ball hits the ground? So we know all this stuff. We also know x final. We just figured that out. And we are trying to find Vx final and Vy final. So velocity means vector, so we need the x component and y component of the final velocity. Fortunately, the x component is super easy. It doesn't change during the entire motion, so the final x velocity is the same as the initial x velocity. That was 22.98 meters per second. So really our only mathematical job is to figure out Vy final, and that's not too hard either, because we can just use Vy final equals Vy initial plus Ay t. There are other ways we could have done it, but all those other equations would have been more complicated. This is the easiest one to use. So Vy initial was it. 19.28. A is negative 9.8 meters per second squared, and T was 5.712 seconds. So Vy final is negative 36.7 meters per second. Again, that negative sign is telling you it's pointing downward, which makes sense because the ball went up but reached the peak and then falls downward. So that's why we've got a negative sign for its velocity vector. So if we write the final velocity vector in component form, it equals 22.98. I guess, 22.98, comma, negative 36.70. Or if we rounded it to correct significant figures, 23, negative 36.7. Now that's component form. We might also want to express this in magnitude angle form. So the magnitude is given by the Pythagorean theorem. That's 43.3 meters per second. And angle is going to be 57.9 degrees below the horizontal, or below the x-axis. So notice in the previous example, our final speed and angle were the same as the initial speed and angle. That's because the motion was symmetrical. It started and landed at the same height. This problem is asymmetrical. You land at a lower elevation than you start, and that gives an increase in speed. Later on, we're going to talk about energy, and we'll see that one way to understand where this extra speed comes from is that it is energy that came from a change in gravitational energy. The fact that you land lower than you start means that gravity has given up some of its energy, and that has gone into extra speed of the object. So we'll learn about that in a few weeks.